And hi, my name is Amirul Ashraf Shamsul Baharim, matrix number CE230123. So I will present about introduction and theory. So for the introduction, a filter is a frequency selective network that favors certain frequencies of input signal at the expense of others. There are three very common types of filter, which are the low pass filter, the high pass filter, and the band pass filter. The difference between active and passive filter is that an active filter uses active components like transistor and op-amp for the filtering of electronic signals and need an external source of power for its operation. Designing filters requires selecting the value of RNC that will satisfy two requirements, which is the bandwidth and the gain. So for the theory related to circuit design. Active fourth order bandpass active filter is made up of many discrete components, which is resistor and capacitor. In the conventional design process, the value of those components are calculated by fixing the values of some components and finding the others in order to satisfy the design specifications. But the use of this method limits the freedom of the design. The basic structure of the fourth order band pass active filter involves cascading multiple filter stages, which is called second order sections, together to achieve the fourth order response. The basic component for fourth order band pass active filter is op-amps, which building blocks of the active filter circuit. Multiple op-amps are used in the cascaded stage. Resistor and capacitor determine the frequency response of each filter stage. The operational principle for fourth order is the first op-amp stage is configured as second order band pass filter. So for the manual calculation, since we do fourth order, then n is 4 in Bato's polynomial table. N equal to 4 is 1 plus 0.765s plus s power of 2 and 1 plus 1.848s plus s power of 2. So so we determine both of them, which is df1 1 plus 0.765s plus s power of 2, and df2 is 1 plus 1.848s plus s power of 2. So for the low pass filter, so we take the value of df1, which is 0.765 equal to 3 minus AV01. So it's the same for AV02. So we take the value of df2, 1.848 equal to 3 minus AV02. So for the AV1 we get 2.235, and for the AV2 we got 1.152. So then we need to find RF. So take the AV01, 2.235 equal to 1 plus RF of per 1K. So we get 1235 ohm. So for the closest standard resistor is 1200. For the AV2, 1.152 equal to 1 plus RF per 1K. So we get RF2 152 ohm. The closest resistor in 150 ohm. So if C is 1 micro and FH is 5 kHz. So 5 kHz equal to 1 per 2 pi R multiply 1 micro. So we get the resistor 31.83 ohm. The standard resistor is 30 ohm. The calculation for high pass filter is basically the same as low pass filter. As you can see, RF3 is 1200, same as RF1. For the RF4 is 150 ohms, basically the same as RF2. So the only difference is their frequency, which for high pass is FL equal to 500 Hz. So 500 Hz equal to 1 per 2 pi R multiply 1 micro, so we get the resistor 318.3 ohm. So for the standard resistor, the closest is 330 ohm. Okay, for non-inverting, so to find AV, just multiply every AV for from low pass filter and high pass filter. So just do the calculation. 90 equal to 6.629 AV05. So ni lah. Just rearrange it. So we get 13.5763. Okay, so to find RF5 is 13.5763 equal to 1 plus RF5 per R1. So we get RF5 12.5763 R1. So if R1 is 12 ohm, so just RF1 equal to 12.5763 multiplied with 12. So we got 150.915 ohm. The standard, the closest is 150. So when gain is 90, value dB, 20 log 10 multiply absolute value. So just 20 log 10 multiply 90, so we got 39.08 dB. So that's all for me. Thank you.
So this component is the component required for the bandpass filter. We use different values and unit of resistors and add unit of 1 microfarad capacitor and 5 open LM741. So this is our bandpass filter. The first two circuits are the second order low pass filter. When combine two circuits together, it will become four order low pass filter. The same concept also used for high pass. The two second high pass filter combined, it will become four order high pass filter. Then it connect to non-inverting amplifier. And then we can get a result of frequency response. Then we find the mid gain. Mid gain is 38.7 in here. Then we find the cutoff frequency. Cutoff frequency is 38.7 minus 3. It will become 35.7. 35.7. So we can find the low cutoff frequency, that is 496. Then we find the high cutoff frequency, that is also 35.7. Okay, this 5.14K. Then we label it. The purple color is mid gain, and this is the gain for cutoff frequency, and this is the low cutoff frequency and high cutoff frequency. Then we do slope analysis. This low cutoff frequency and 0.1 of cutoff frequency is 1 decade. Then it increased 76 dB per decade. And also for high cutoff frequency, the 10 of high cutoff frequency is 1 decade. Then it decreased 75.8 dB per decade. Then the number is close to 80 dB per decade. That's 4 order bandpass filter.
Assalamualaikum warahmatullahi wabarakatuh. My name is Azizul bin Muhammad Jamadi and my matrix number is DE210051. I'm from group 3 and from section 2. So for my part, I will present about the result from experiment testing in laboratory, the frequency response and also the slope analysis from the graph. Okay, so first thing first, we can see that here we have the table that we already collect data from the laboratory. We set the frequency from 100 Hz to 10 kHz, and then we collect the data from for V out and V in, and then from that we can get the value for gain unitless and also gain in dB. Okay, so after collect the data, the next step is we need to plot the frequency response, and then where the x-axis is frequency and the y-axis is in the gain dB. And then we can see that this is the shape of the our graph in laboratory. Maybe it's not perfect, but then after that we need to do the slope analysis. Okay, that is the next step. Okay, how we need to do the slope analysis? First thing first, we need to make the line for the mid gain, that is 37.53 dB, After that, we need to minus 3 dB, that is 34.53 dB. And then from that, we can get the value for low cutoff frequency and high cutoff frequency. Okay, to get this value for FL, that is low cutoff frequency, I plot also this table, I plot in the Desmos graph, and then I made the line to see the value. That is, it shows that the low cutoff frequency is 490 Hz for the FL, and then the F hash, the high cutoff frequency is 5.396 kilohertz. Okay, that is the data that we got from this table, and we can say that our group not actually can get the perfect value like simulation, because maybe we have problem with our component, or maybe the hole in the breadboard or anything else. But we try our best to figure out and calibrate, and also try and error, just to make sure we got the result. Okay, that's all from me. Thank you.
Assalamualaikum warahmatullahi wabarakatuh. My name is Nur Syairah binti Muhammad Saleh with metric number DE210050. I will continue for analysis and discussion. So based on the analysis of the result, we can see that the simulation and theoretical result are very comparable. So the simulation result approximately match the theoretical result, but the measurement result deviates slightly from the both theory and simulation. So as you can see from the table, the given value for mid gain is 90 unitless. Same goes to the simulation, but for the experiment, the mid gain we got 75. It's slightly different, and for the mid gain, we calculate mid gain in dB. Given value, we got 39 dB, and minus 3 dB we got 36. For the simulation, mid gain in dB we got 38.7, and minus 3 dB we got 35.7, and also slightly different for the experiment value. Same goes to the low cutoff frequency and the high cutoff frequency. So from the result obtained, we can see that both simulation and experiment are slightly lower than the theoretical and the simulation values. So the actual reading output signal is difficult to read because of the noise. Okay, so for the conclusion, we gain a deeper understanding of the advantages and challenges associated with the fourth order bandpass active filter. The challenge encountered during the design and testing phase highlight the importance of careful consideration of component values, tolerance, and potential source of the error in the practical circuit. So overall, the first order bandpass active filter experiment not only deepen our understanding of the filter design, but also hone our skill in practical circuit implementation and troubleshooting. That's all from our group. Thank you.